AP Calculus AB, Unit 10, Day 8 lesson. So we're going to talk about solids of revolution some more. I'm going to focus on the shell tree ring method, which I've shown you, but I'm going to show you again. And then we're going to get some practice with it on today's assignment, as well as the disc washer method. So there's two approaches. They both should give you the same answer. We're just slicing the same volume up different ways. If it's a vertical slice, then everything's going to be in terms of dx, regardless of what kind of slice it is. If it's a horizontal slice, anytime, it's going to involve y. If you want to get disc washers, you slice it perpendicular to the axis of rotation. And if you slice it parallel, you're going to get these tree rings, like the tree trunk I was explaining the other day, on cylindrical shells. Now, the disc washer method, pi r squared times the thickness, dx or dy. If there is a hole in it, then you got to subtract a smaller disc from it. This is the disc. This is the disc approach, and this is the washer approach. Okay. Now shells. This is sort of an example of one single shell. They're nested shells. They fit within inside of each other, and they have to be parallel to the axis of rotation. So this is the axis of rotation. So they go along it. Now, if you were to take one shell here, let me see if I can do one small enough to fit on the video. So this is a shell, right? This is one shell. There's going to be a bunch of other shells that fit in it or outside of it. So this is one shell. To find the volume of the shell, it's very thin. That's where the dx or dy is going to be. But to find the volume, what we do is we take the area and multiply times the thickness. So if you open this up, you just get a rectangle. So, I mean, it's simple as that. You open it up, you get a rectangle. It has a thickness still. The rectangle has the same height as the shell had. This distance up here is going to be the distance around the whole top of the original shell. This right here becomes that dimension of the rectangle. And so it involves the radius and it's the circumference. It's 2 pi r. And then the thickness is going to be dx or dy, depending on the orientation of the slices. So the volume of one of these shells, one tree ring, one shell, is just a rectangle, 2 pi r times h times the thickness. Which is dx or dy. If you want all of them, well, then we're going to take one of them and accumulate them all with an integral. So that's the volume of a shell. So it's that. Try and keep that in mind when you do these, so you don't have to try and memorize it. If you try and memorize these, I guarantee you're going to mess them up really bad. It's going to be just obvious that you don't know what's going on. It's better to visualize it, go back to the basics. The geometry is pretty simple when you boil it down. So it's rectangle times thickness, right? So let's try a few examples both ways, disc washer and shells. Okay, we'll start with the shell tree ring approach. So pictures are drawn for you. We still want to, I find it very helpful to draw the reflection of the shape over here so we can kind of visualize a little more of the whole three-dimensional shape. Now, if we want shells we want to slice it parallel to the axis of rotation. And then, you kind of draw this and you can see the shell. There's the shell right there. There's one shell. Now everything should be based off this original region over here. This is just for looks. This is just to kind of visualize it. Everything, limits, dimensions, everything should be over here. So like we said, if we slice the shell open, you get a rectangle, 2 pi r times h. The thickness is going to be dx this time because it's a vertical slice. The limits are going to go in the x direction, 0 to 4. For shells, we stop at the edge of the hole. So we don't take the approach. The disc washer, it's a big disc minus a small disc. We have to take out that part that got counted to get the hole correct. For shells, we just only integrate up to the edge of the hole and don't integrate into it, so we don't have to subtract it later. So the radius of the shell could be up here, it could be up here, so it could be touching this curve, it could be touching this curve. The radius has nothing to do with the curves. The radius is just being slowly changed, okay? It's x right minus x left, and x right is 6, and x left is just whatever x value are. We're going to start at x equals 0, the biggest radius, and we're going to gradually change x until it gets to 4. That'll give us the smallest radius. When x is 0, you get the biggest radius of 6. When x is 4, you get the smallest radius of 2. But that's it, 6 minus x. So the radius of a shell is always just going to be x or y, plus or minus a number. It's never going to involve these functions at all. The height of the shell is where the curves come in. So this is going to be y top minus y bottom, y top minus y bottom, right? Then we want it in terms of x, so y top is the square root of x, y bottom is 0, so we can just ignore it, and then put the dx here. So this is it. That's your setup, and that's what I'm going to focus on today. And I'm not going to do all the busy work afterwards, but we could do it on our calculator. Let's try that. Let's get good. You guys probably could all get better at your calculator faster, more accurate. 2 pi, math 9, parentheses, 6 minus x, square root of x, comma 0, comma 4. Should be fast. You should know where things are. 120.637, round truncated 3 decimal place actually is the same this time. Okay, now we're going to do the same shape, but we're going to use the disc washer method. So we're going to draw a picture again real quick. I think having a nice picture is worth the time. If you don't, these problems are hard enough anyways. So this time I'm going to slice perpendicular to the axis of rotation, right? And when you do that, you get these flat kind of pancake disc slices. And there's a hole in the middle. So we have a big radius that goes all the way to the axis of rotation, and then we have a little radius. So the volume of one slice, it's just a short cylinder. It's a circle times the thickness, pi r squared. Thickness is dy because they're horizontal slices, minus pi little r squared dy. So that's going to be that hole. The limits are going to be in the y direction, so 0 to 2. The big radius is x right minus x left. And x right is the axis of rotation, which is at 6. X left is over here. In terms of y would be y squared. 6 minus y squared squared dy. So I just write all over this picture. This is little r, it's x right minus x left. I mean, I would write this stuff down. X right is 6. X left is this, which is always 4. So it's just going to be 2 all the time. That's your setup. Let's try it on the calculator to see if we get the same answer. So we're going to do pi, math 9, parentheses, 6 minus x squared. We're going to put x's for the y's. Close parentheses, squared, comma x, comma 0, comma 2, minus pi, math 9, 4, comma x, comma 0, comma 2. Should be able to type it in that quickly. There's the answer, 120.637. Same answer. Got it. Now, which one was easier? I don't know. I mean, I kind of think the shells were kind of a little simpler, but that's it's up to you. But on your test, I'm going to make you guys do them both ways. So let's try a couple more. Both ways. We'll start with the new method first. So we'll start with the shell method. We have the sideways parabola. We have a line. The intersection is given to us. This is 0, 0. This is, well, let's see, x-intercept of this line, which would be y equals 0. This would be 2, 0, just in case we need that. So this is the visual region. We're going to spin it around y equals -2. So what I do is I try and get these corners first and then connect them with lines. That, to me, that's quickest way. So then if we want shells, we're going to slice it parallel to the axis of rotation. So you're going to be in line with the axis of rotation. And we're going to get one shell. Okay? So the volume of one shell is, if you slice this open, you get a big rectangle, remember? The height, and then 2 pi r for this unit. So it's 2 pi r h. And the thickness is going to be dy this time, because they're horizontal slices. The limits, I'm going to write down here, the limits are going to be in the y direction, always based off of this. So 0 to 2. That's it. The radius is going to just involve x or y plus or minus a number, possibly. Y top minus y bottom. Now, y top is whatever y value we're at in our slicing, and y bottom is -2. So it's going to be y minus -2. The height is the thing that involves the curves, and this is sideways this time. So the height is x right minus x left, and that changes based off the curves. The radius doesn't. The radius is, we're just gradually changing it as we integrate. The height depends on these curves. X right in terms of y would be y plus 2, and x left in terms of y would be y squared. And that's your setup. Put in our calculator, see what we get. So we're going to do 2 pi math 9 parentheses x plus 2 parentheses x plus 2 minus x squared close comma x comma 0 comma 2. There's the answer. 58.643 rounded or truncated, 3 decimal accuracy. Comes out the same this time. Now let's try the same problem with your beloved disc washers. Whenever I say that, I feel like I'm saying dishwasher. Disc washers. Now, the picture, we're going to do the picture real quick. Recreate the picture. And I think it's worth it to do these two approaches on separate pictures, because it's just going to get too messy. Now, if you want disc washers, we're going to slice perpendicular to the axis of rotation. Okay? Now, here's one of the bad things about this problem is that we're going to have to do a separate set of disc washers over here, because what determines that hole changes. So we're going to have to do 2 different sets of disc washers. And that's why shells would be awesome on this one. So the first ones, we're going to go to, we're going to go from 0 to 2. So pi r squared dx minus pi little r squared dx. And we go 0 to 2. Then we're going to have to add another set of them from 2 to 4. 2 to 4, pi r squared dx minus pi little r squared dx. 2 to 4. Now, these big r's and little r's are not the same thing. This is just my really generic, just saying there's a big radius and a small radius. Okay, so for these first ones, this is your big R, and this is your little r, and it's y top minus y bottom. Y top in terms of x is the square root of x minus y bottom is -2. So square root of x minus negative 2 squared dx. The little radius is y top minus y bottom. This is length right here. Y top is 0, y bottom is negative 2. So that accounts for the first set of disk washers, plus 2 to 4. This is the big radius here, y top minus y bottom. Y top is the square root of x still. So the big R actually stays the same for both of them. It's the little r on this one that changes. So little r is y top minus y bottom. Y top is along this line in terms of x is x minus 2. And then we're going to subtract the negative 2. So that's the setup. I mean, come on, shell method was so much easier. Now you got to type this all on your calculator. Now this will become positive 2, right? So that'll just be a 4. That'll become plus 2. Those will cancel each other out, so we'll just have an x squared. Plus, 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 plus. Let's see if we can enter all this stuff in our calculator and get the same answer. I'm scared that I'm going to make a mistake. It's just way more stuff to type in. Pi, math 9, parentheses, square root of x, close, plus 2, parentheses, close, squared, comma x, comma 0, comma 2. So that's the first one, minus pi, math 9, 4, comma x, comma 0, comma 2. So that's that one, plus pi, math 9, square root, parentheses, square root of x, close parentheses on square root, plus 2, close parentheses, squared, comma x, comma 2, comma 4, minus pi, oh my gosh, math 9, x squared, comma x, comma 2, comma 4. So I think I typed it all correctly. It's probably going to take my calculator a little longer to calculate too. I mean, so I think I got everything in there correct. Yep, same answer. It's a good sign. But this is something to start to consider. Just because you like dishwashers, because that's the one you've been doing longest. I mean, that was a lot of work. That was a mess. I mean, and we hoped we didn't make a mistake. This was way simpler. So sometimes one will have an advantage over the other. Okay, this one, we're going to do shells first. This is our region. Sideways, it's parabola. Then top half a sideways parabola. So rotating around this line over here. Okay, so if we're going to do shells, we want to slice it parallel to the axis of rotation. So we'll just draw one slice kind of equidistant from the axis of rotation and kind of sketch a shell. The volume is, if we cut this open, it's going to be 2 pi r h dx. We're going to integrate in the x direction, so left to right, 0 to 1, just on the original region. That's always going to be your limits for any integration problem that are based off some region. Always is based off that region. Now the radius is going to be x right minus x left. It's going to be whatever x value we're at, because we're going to start at x equals 0 and gradually get to x equals 1, and just slowly making x bigger. But we do have to subtract negative 2 because that's going to make the radius. It's going to give the radius part of size. So it's going to be x plus 2. The height is the thing that depends on the curves. It's going to be y top minus y bottom. This one's changing with the curve. So y top is the square root of x. Y bottom is x squared. Square root of x minus x squared dx. Done. I mean, I don't know. I'm kind of leaning towards liking shells better than dishwashers. Okay, let's see if we can calculate this. 2 pi, math 9, parentheses, x plus 2, parentheses, square root of x, close parentheses, and square root, minus x squared, close parentheses, comma x, comma 0, comma 1. This should be it. 5.131 round truncated 3 decimal place comes out the same this time. All right. Let's try it the old way, or the original disc washer way that we've practiced more. And I'd say it's kind of more mainstream. So we got to slice it perpendicular to the axis of rotation. Now we get one set of disc washers this time, which is nice. We're not going to have to deal with all the headache of the last one. So we have pi big R squared dy. Now, one of the side effects of this is everything's going to be y, which I think makes it a problem a tiny bit harder than x. Pi little r squared dy. Then we're going to integrate. So we're integrating in the y direction 0 to 1. The big radius, everything's based off this. So the big radius is x right minus x left. X right minus x left. So x right in terms of y is the square root of y. Right? Square root of both sides, plus or minus. We want the positive one because we're dealing with the right half of the parabola. Square root of y. X left is negative 2. So the first radius is square root of y plus 2 squared dy. The little radius right here is x right minus x left. It's this x right in terms of y is going to be y squared minus x left is negative 2. So that's going to be y squared plus 2 squared. Don't forget the squared. So that's your setup. That's your setup. So we're going to just plug this in the calculator and see if we get the same answer. So we're going to do pi math 9 parentheses square root of x plus 2 parentheses squared comma x comma 0 comma 1 minus pi math 9 parentheses x squared plus 2 close parentheses squared comma x comma 0 comma 1. See if we pulled it off correctly, typed it in correctly. Got it right, 5.131. Nice. So today's assignment is this worksheet, and I want you to do these both ways, each problem both ways. I might redraw the picture. Otherwise, carefully try and draw the slices away from each other. If you're going to do one over here and do one over here, if you want to try and fit them on the same picture, but it's going to get busy. You're going to go ahead and evaluate them on your graphing calculator. So the hard part is setting them up, and then you're going to type them in your calculator. You don't have to do all the detailed work of integrating by hand. But I want you to try all of these both ways. This is going to probably be the hardest part for a lot of you guys on this next test. And this is it. This is, there's going to be a bunch of solids of revolutions. You're going to have to do shells and washers. Okay. Now, part A is dx. So it might not be shells every time. And part B is dy. It's depending. I want you to do part A, which might be shells, might be washers. And then do part B, might be shells, might be washers. Depends on the orientation of the shape and the rotation. So if you are here, I'll try and do this first one, start this first one with you. If you are going to do them on the same picture, you got to be extra neat, okay? So dx, you might do over here, vertical slice, and that's going to be a disk. And then dy, you might do up here, and that's going to be your shells, right? So keep them away from each other so that they don't, you can keep things straight, So, all right, that's it. Try them out.